What if the most important thing a machine ever did was choose to die? On September 15th, 2017, a spacecraft about the size of a school bus turned its antenna toward Earth and aimed the rest of itself straight into Saturn. It sat nearly 1 billion miles away. It was also, by every measure that mattered, perfectly healthy. Its instruments worked. Its computer still answered. And within a few hours it would be gone, torn to pieces in the upper air of the planet it had circled for 13 years. Nobody pulled the plug by accident. There was no failure, no collision, no slow fade as the batteries gave out. The people who built this spacecraft pointed it at a planet and flew it in on purpose, and they had been planning the exact hour of its death for years. Here is the part that stays with me. As it fell, it kept working. 8 of its instruments were switched on, tasting an atmosphere no probe had ever reached, sending every reading home in close to real time. The machine narrated its own destruction, second by second, until the last instant its antenna could hold a thread of contact with Earth. Then the thread went quiet. The spacecraft was Cassini. For 2 decades, it had been the most successful explorer we ever sent to the outer solar system. It crossed more than 2 billion miles to reach Saturn. It set a lander down on a moon farther from Earth than anything humanity has ever landed on, before or since. It watched storms wider than our entire planet churn through Saturn's clouds for more than a decade. It found oceans in places no one expected oceans to be. And then, with its work nowhere near finished, the people who loved it most decided it had to die. The reason was a moon, a small one, barely 300 miles across, white as bone, sealed under ice, orbiting out at the cold edge of the Saturn system where almost nobody was looking. Its name is Enceladus. By the time we are finished tonight, that name is going to carry far more weight than it does in this first minute. If you enjoy these journeys into space mysteries and the strange edges of the cosmos, hit subscribe and settle in. This is a long one, and it is meant to be. There is one more detail I want to put in your hands before we begin, because it bends the shape of everything that follows. When the signal confirming Cassini's death reached Earth, the spacecraft had already been gone for 83 minutes. Saturn sat so far away that the final transmission needed an hour and 23 minutes simply to cross the distance home. We did not watch it die. We received its death long after the moment had passed, the way you might read a letter from someone already in the ground. So we are going to do something a little strange over the next 2 hours. We are going to walk backward into those 83 minutes and ask why any of it had to happen. Because the month NASA confirmed that small ice moon might be able to hold life was the same month the team began steering Cassini toward its grave. Those 2 facts are not a coincidence sitting near each other. They are the same fact, seen from 2 ends. And why they are the same fact is the whole story. Consider Cassini as it was at the beginning, not at the end. A spacecraft roughly the size of a school bus, 2 stories tall, wrapped in gold-colored insulation, bolted to the top of a rocket in Florida on a humid autumn night. Fully fueled, it weighed about 5.5 tons. It was the largest and most complicated machine anyone had ever tried to send to another planet. And on October 15th, 1997, at 43 minutes past 4 in the morning, a Titan rocket lifted it off the pad at Cape Canaveral and threw it toward the outer solar system. Saturn sits, on average, nearly 1 billion miles from Earth. That number is hard to hold in the mind, so let me put it somewhere your body can feel it. If you could board a passenger jet and fly it in a straight line towards Saturn at the speed it crosses an ocean, you would not arrive in your lifetime, and neither would your grandchildren. The flight would take more than 150 years without ever landing. Saturn is not a place you visit. It is a place you launch an expedition toward and quietly hope to outlive. Cassini was far too heavy to fly there directly. No rocket then or now could throw 5.5 tons straight at Saturn and have it arrive with fuel to spare. So the engineers did something that still sounds like cheating the first time you hear it. They aimed the spacecraft the wrong way. They sent it inward, toward the Sun and toward Venus, and let the planets themselves do the throwing. The trick is called a gravity assist, and the route Cassini flew has a name only an engineer could love. Venus, Venus, Earth, Jupiter. 2 swings past Venus, 1 past Earth, 1 past Jupiter, each pass stealing a sliver of speed from a planet's motion and handing it to the spacecraft. In April of 1998, Cassini passed within about 175 miles of the surface of Venus and came away roughly 16,000 miles per hour faster than it had been. It looped the Sun and did it again in June of 1999. That August it came home for a moment, swinging past Earth close enough to skim the edge of space, borrowing one last push from the planet that had built it. Then out to Jupiter in December of 2000 for the final shove toward the rings. By the time the slingshots were done, Cassini had traveled about 2.2 billion miles to cover a straight-line distance less than half of that. It took the long way on purpose. 7 years of falling around the inner solar system to build the speed it needed to reach the outer one. To feel 2.2 billion miles, picture driving it at highway speed and never once stopping. Not for fuel, not for sleep, not for anything. You would still be behind the wheel 4,000 years later. The spacecraft managed it in 7 by letting 4 planets throw it. The last of those throws, at Jupiter at the very end of 2000, was not only a push. Cassini spent weeks studying the giant planet on its way by, trading observations with another NASA spacecraft, Galileo, that was orbiting Jupiter at the time. For a brief window, we had 2 robotic explorers working the same planet from different angles, a small moment of cooperation between machines hundreds of millions of miles from the people who built them. Then Cassini fell away towards Saturn, and the long quiet set in. Picture those middle years of the cruise. A spacecraft alone in the dark, the Sun shrinking to a bright star behind it, the planets gone. Nothing ahead but cold and distance, and the faint thread of a radio link to a world it could no longer see. It crossed that emptiness for years, asleep in most of its systems, waking now and then to check that its instruments and its sleeping passenger Huygens were still well. There is a particular loneliness to deep space that we almost never picture. Cassini lived in it longer than most of us live anywhere. It reached Saturn on the 1st of July, 2004, and the arrival was its own kind of terror. To be caught by Saturn's gravity instead of sailing straight past it, Cassini had to fire its main engine for 96 minutes, braking hard at the exact moment it threaded a narrow gap between 2 of the rings. The plan had no second attempt built into it. If the engine misfired, if the timing slipped, if a single ring particle the size of a pebble struck it at orbital speed, the whole thing was over. 20 years of work erased in an instant, 1 billion miles from anyone who could lift a finger to help. The engine lit. The burn held. Cassini slid into orbit and became the first machine in history to circle the ringed planet. The names that machine carried were not chosen at random. Cassini took its name from Giovanni Cassini, the astronomer who, more than 3 centuries earlier, had picked out the dark gap that split Saturn's rings and discovered 4 of its moons through a simple telescope. The lander took its name from Christian Huygens, who in 1655 became the first person to see Titan, and who worked out that the strange handles around Saturn were in fact a ring. 2 men who had squinted at a fuzzy point of light through hand-ground glass, lending their names, 3.5 centuries on, to the machines that would finally go and stand among the rings they could only dream about. And it was not one country's project. Cassini was built and flown by the American, European, and Italian space agencies together, the labor of thousands of scientists and engineers across more than 24 nations, one of the largest international undertakings in the history of science. It took a meaningful slice of an entire planet to send a single spacecraft to another one. And the moment it arrived, it began paying us back. On the night it slipped through the rings, Cassini turned its cameras on them from closer than any eye had ever been and sent home images so sharp they redrew the textbook on the spot. Structures in the rings that had looked smooth from Earth broke apart into waves, gaps, braids, and delicate ripples, a whole hidden architecture revealed in a single pass. Before it had even settled into its first full orbit, the spacecraft had already shown us a Saturn no one had ever seen. 6 months later, it pulled off something stranger still. Bolted to its flank for the entire journey had ridden a second craft, a European-built lander called Huygens, asleep the whole 7 years. On Christmas Day of 2004, Cassini let it go. Huygens drifted for 3 weeks, and then on January 14th, 2005, dropped into the thick orange atmosphere of Titan, Saturn's largest moon. It parachuted down for 2 hours and 27 minutes and settled softly onto a surface no eye had ever seen. It kept transmitting from the ground for another 72 minutes before the cold and the distance finally silenced it. To this day, it remains the most distant landing humanity has ever achieved. We will come back to Titan because what waited down there matters more than almost anyone understood at the time. Then came the heart of the mission. 13 years of orbit. 13 years of Cassini swinging around Saturn on long looping arcs, ducking past one moon and then another, watching the seasons turn on a world where a single year stretches almost 30 of ours. It powered all of this not with sunlight, which is far too faint that far out, but with a slow trickle of heat from about 70 pounds of plutonium decaying inside it, a nuclear battery built to outlast the mission many times over. That detail matters, and we will return to it, because the thing that kept Cassini alive is also part of why it had to die. What it did with those years is the reason an entire generation of scientists fell in love with it. It counted new moons that no telescope had ever resolved. It flew straight through the icy spray of geysers and tasted what they were made of. It tracked lightning inside storms that could have swallowed continents whole, and it watched the rings ripple and warp as though something kept brushing a hand across them. For the people who ran it, Cassini was never really a tool. It was a companion that happened to live near Saturn and mailed a postcard home every few days. It photographed a hurricane sitting on Saturn's North Pole, locked inside a strange six-sided cloud pattern, wide enough to set 2 Earths side by side within it. No one had ever seen a storm hold a geometric shape like that, and we still argue about how it stays so sharp. It mapped the rings from closer than any instrument ever had, and found them stranger and more alive than the smooth bands they look like from here. Season by season, it watched the blue of Saturn's northern hemisphere warm into gold as the planet leaned slowly toward the sun across years of patient watching. It caught Saturn throwing a tantrum too. Late in 2010, a colossal storm tore open in the planet's northern half, a churning white cloud that grew and grew until it had wrapped itself the entire way around Saturn, a belt of storm tens of thousands of miles long, encircling the whole world. These great northern outbursts come roughly once in a Saturn year, which is to say about once every 3 decades, and Cassini happened to be right there, in orbit, when this one broke. It tracked the storm for months as the head of it slowly caught up with and devoured its own tail. To put the scale in human terms, the storm grew long enough to wrap around a planet you could pour more than 700 Earths into. No one had ever held a front row seat to a planet-circling storm on another world. Cassini did, for the simple reason that it was there, year after patient year, when the rare thing finally happened. It studied the rings themselves more closely than anyone ever had, and they turned out to be far stranger than the smooth painted bands they resemble from Earth. The main rings stretch about 175,000 miles across, wider than 2/3 of the way to our own moon, and yet in most places they are only around 30 feet thick. Picture that for a moment. If you shrank the whole ring system down to the width of a football field, the rings would be thinner than a single sheet of paper laid flat across the grass. They are made of countless chunks of ice, most no bigger than a pebble or a boulder, each one a tiny moon on its own orbit, all of them circling Saturn in a sheet so flat and so wide it barely makes sense. The moons were stranger yet. Cassini flew past more than 60 of them across its mission, and a few of those flybys left scientists genuinely unsettled. There is Iapetus, a moon painted in 2 colors, one hemisphere dark as old coal, and the other bright as fresh snow, with a hard line between them as though someone had dipped half the world in ink. Running along its middle, almost exactly around the equator, Cassini found a ridge of mountains roughly 8 miles high, a raised seam circling the moon like the welded edge of a walnut. Nobody has fully explained how it got there. Saturn turned out to be ruled not by one planet, but by a whole menagerie of small worlds, each with a secret of its own. And the smallest moons did the strangest things of all. Tucked into gaps within the rings, Cassini found tiny shepherd moons herding the ice around them, their faint gravity combing and carving the ring material into knife-sharp edges and standing waves. One of them, a little moon named Pan, turned out to look almost exactly like a ravioli, a small, round body wearing a smooth, raised ridge of swept-up ring material around its equator, as though it had been spinning through the rings gathering a skirt. Another, Daphnis, raised delicate waves in the ring edges as it passed, like a boat leaving a wake. These were not the grand spherical moons of the textbooks. They were odd, specific, characterful little worlds, each one sculpted by the exact place it happened to live. On one particular day in July of 2013, Cassini turned and looked back at us. From its place beside Saturn, it photographed the rings lit from behind, and there, in the dark gap between them, hung a single pale dot. That dot was Earth. Every person who has ever lived, every argument and every act of kindness in the whole of human history, all of it folded into one point of light, smaller than a single pixel, caught by a camera nearly 1 billion miles away. To make that distance land, consider that the light carrying our reflection took well over an hour to reach the spacecraft. The team called it the day the Earth smiled, and people walked outside in the evening and waved at the sky, knowing something out near Saturn had its lens pointed back at them. There is one more thing worth understanding about those 13 years, because it sits underneath the ending like a held breath. Every postcard Cassini sent had to cross that same near billion miles of empty space, and by the time it reached us, the signal was almost unimaginably faint, weaker than the bulb inside a refrigerator, gathered up by giant dish antennas the width of a baseball diamond planted in California, Spain, and the Australian outback. And the conversation was never live. As Saturn wandered farther along its orbit, a command radioed from Earth took well over an hour to arrive, and the spacecraft's answer took just as long to come back. You could not fly Cassini in the moment. You could only send instructions into the future and wait, sometimes for hours, to learn what the machine had already done with them. Hold that thought. It becomes the whole shape of the final day. And this is where I want to slow down, because everything I have told you so far is the version of the story most people already carry. The triumphant mission, the little explorer that could sailing home its postcards from the rings. All of it is true, and all of it is the version that gets told. But underneath the triumph sits a quieter assumption, one so ordinary that almost no one ever thinks to question it. The whole rest of this story lives inside cracking that assumption open. The assumption is simple. Spacecraft are tools, and we use tools until they break. That is how it has always gone. A probe launches. It works for as long as its parts and its power hold out. And then, one day, it falls silent. Sometimes the power source decays past the point of usefulness. Sometimes a part fails in the deep cold, or the craft drifts so far that its voice thins into noise and we can no longer hear it. When that day comes, we do not grieve the hardware. We log the end of the mission, we thank the people who flew it, and we let the dead machine coast onward as a kind of silent monument to itself. The Voyager probes are the clearest case. Launched back in the 1970s, still faintly alive at the ragged edge of the solar system, they are slowly winding down. Sometime in the next decade or so, the last of their power will drain away, and they will go quiet for good. And then they will simply keep going. Two dead spacecraft coasting between the stars for millions of years, long after the last person who built them is dust. No one will steer them. No one will end them. They will fall forever. That is the ordinary fate of a deep space machine. You ride it until it dies, and then you let it drift. Cassini did not get that ending. And here is what should stop you, because it stopped the people who knew that spacecraft best. When the end came, Cassini was not broken. Its instruments were sharp. Its cameras still focused. Its computer answered every command sent across the billion miles between us. By the standard of any other mission, it was healthy, and it was good for years of work yet to come. There was no failure to write down, no dead part, no lost signal. The people who built it killed it anyway, deliberately. They spent years working out the precise hour to fly a healthy, irreplaceable, multi-billion-dollar spacecraft straight into a planet and let it come apart. No deep space mission had ever been ended that way. You do not destroy a working machine that took 20 years to build and deliver unless something has gone badly wrong. or unless that machine has stumbled onto something so important that its mere survival has turned into a threat. Pull on that single thread, and the triumphant little story unravels into something far stranger. Because Cassini had become a threat, and the thing it threatened was a moon. And then the data started coming in. To understand how a moon could force the death of a spacecraft, you first have to understand how little anyone expected of this particular moon. Enceladus is small, barely 300 miles across, a white pebble of ice orbiting in the outer cold of Saturn's system. You could set it down inside the borders of the state of Arizona and still have room left over. By every rule we thought we understood, it should have been dead. Small worlds bleed their heat away fast. They freeze solid early and stay that way for billions of years, silent and still. Nothing moving, nothing warm. Enceladus was supposed to be a frozen marble, and for a long time that is exactly what everyone took it to be. The first crack in that assumption arrived in February of 2005, and it came from an instrument that cannot even take a picture. Cassini carried a magnetometer, a device built to sense magnetic fields. As the spacecraft swung past Enceladus, the magnetometer caught something odd. Saturn's magnetic field, which should have streamed past the little moon clean and undisturbed, was being shoved aside, bent around it, as though the moon were wrapped in something, a thin haze or an atmosphere that was nudging the field out of its path. For a dead ball of ice, that made no sense. A frozen rock has nothing to push back with. Something around Enceladus was breathing. At first, the team could not find it. They tried to catch the haze directly. One instrument watched a distant star as it passed behind the moon's edge, hoping the starlight would flicker as it cut through any atmosphere clinging to the surface. The starlight did not flicker. They aimed it across the equator and got nothing at all, a flat and disappointing nothing. If Enceladus was venting something into space, it was not coming from the warm middle of the moon where you would expect it. It was coming from somewhere else. So they turned the cameras toward the one place no one thinks to look on a world like this: the bottom, the South Pole. What they found there should not have been possible. On a sunlit world, the equator is the warm part, because it catches the most direct light, and the poles are the cold extremes. Enceladus had it backward. When Cassini's infrared instrument mapped the temperature of the surface, the South Pole came back warmer than the equator. Not by a rounding error. The equator sat at about 316 degrees below zero Fahrenheit, roughly what you would expect for a frozen rock that far from the sun. But cut across the South Pole, and the temperature climbed. In places, it reached 261 below, which sounds impossibly cold until you realize it is some 55 degrees warmer than the equator that gets all the sunlight. Heat was leaking out of the bottom of this moon, and heat has to come from somewhere. When they looked closer at the South Pole, they saw why. 4 long parallel fractures cut across it, deep gashes in the ice running roughly 85 miles end to end, evenly spaced, almost as though something had dragged a set of claws across the surface. The team gave them an informal name that stuck: the Tiger Stripes. Individually, the 4 fractures earned names borrowed from old cities of legend: Alexandria and Cairo, Baghdad and Damascus. 4 warm scars raked across the bottom of a frozen world, and the Tiger Stripes were the hottest places on the entire moon. Whatever was warming Enceladus was pouring its heat straight up through those 4 cracks. This was not a dead world. It was a world with a furnace running somewhere underneath it and the furnace was venting through the floor. But heat has to come from somewhere, and a moon this small should have spent the last of its warmth long ago. So where was Enceladus getting it? The answer is the same force that lifts the tides in our own oceans, cranked up to a punishing degree. Enceladus does not circle Saturn on a clean circle. It is caught in a slow gravitational tug-of-war with a larger neighboring moon called Dione, and that pull keeps its orbit slightly stretched, slightly off-round. So as the little moon swings nearer to Saturn and then farther out, the giant planet's gravity squeezes it and lets it go, squeezes and lets go, on every single lap. The moon flexes. It kneads itself from the inside. And just as a paperclip bent back and forth turns warm between your fingers, all that flexing breeds heat deep in the core, enough to hold an ocean liquid in a place the sun has all but forgotten. The furnace was Saturn itself, working the moon like a hand slowly closing and opening around it. And here is a puzzle that still nags at the people who study this. Tidal heating should not single out Enceladus alone. There is another moon of Saturn, Mimas, that orbits not far away and is nearly the same size. A small ball of ice that by rights ought to feel a similar squeeze. Mimas is the one with the enormous crater that makes it look unsettlingly like a certain space station from the movies. And Mimas, on its surface, shows none of what Enceladus shows. It is cratered, frozen, and still, the very picture of the dead iceball Enceladus was supposed to be. Two nearly identical little moons, neighbors in the same system, and one of them vents a warm sea into space, while the other shows nothing of the kind on its battered, frozen face. We still cannot fully explain the difference. Something in the precise rhythm of Enceladus's orbit, the exact way it flexes on each pass, lit a fire we can watch erupting at its pole, a fire that has never broken the surface of its twin. The line between a dead world and a living, capable one can be that thin and that strangely arbitrary. Then came the image that changed everything. Cassini caught the moon backlit, with the sun behind it, and there, along the South Pole, rising off the tiger stripes, were plumes. Jets of fine spray, more than 100 of them, firing up off the cracks and out into space. The moon was erupting. Not lava, water. Cassini had found geysers on a ball of ice 300 million miles past the asteroid belt, fountains of frozen mist shooting off the bottom of a moon at something like 800 miles an hour, fast enough that much of the spray never fell back down at all. It escaped the moon's weak gravity entirely and drifted out into orbit around Saturn. And here, a much older mystery quietly solved itself. Saturn has a faint, wide outer ring called the E-ring, a tenuous haze of microscopic ice grains that no one had fully explained. Enceladus orbits right inside it. The plumes were the answer. Every eruption flung a little more ice into space, and that ice spread out along the moon's orbit to form the ring. Enceladus was not just sitting inside the E-ring. Enceladus was making it, breath by breath, the way a candle makes its own halo of smoke. Try to stand there for a moment in your mind, the south pole of a moon at the far edge of the cold. Above you, Saturn fills a third of the sky, banded and enormous and silent. Beneath your feet, the ice is cracked into long blue fissures, and out of those fissures the fountains rise, columns of fine crystal climbing hundreds of miles into a black sky, lit silver by a distant sun, falling back as the softest snow that has ever fallen anywhere. There is no sound. there is no wind. There is only the slow, patient breathing of a buried sea, venting itself into space, the way it has for who knows how many millions of years, with nobody there to see it, until a machine from a blue planet flew straight through the spray and held out its hand. So Cassini did something audacious. It flew straight through the plume. More than once. It dropped low over the South Pole and let the spray wash across its instruments at thousands of miles an hour, sampling the eruption directly, tasting what a hidden world was throwing up from beneath its ice. The icy grains slammed into the detectors so hard they vaporized on contact, and the instruments read off what they were made of from the flash. On the deepest of these dives, the spacecraft passed only a few dozen miles above the surface and flew through the densest part of the jets it could reach. It did this with two instruments above all. One, called the Cosmic Dust Analyzer, worked like a catcher's mitt for ice grains. Particles slammed into its target at speeds between roughly 4 and 11 miles every second, vaporizing on impact, and the instrument read off their chemistry from the flash of the collision. The other, the ion and neutral mass spectrometer, drank in the gas directly and sorted it molecule by molecule. Cassini flew the plume in 2008, again in 2009, and returned for one last pass in October of 2015. Each pass came back with a richer and stranger inventory than the one before. That dive in October of 2015 deserves its own moment because it was the boldest of them all. The team sent Cassini barreling through the plume at something like 19,000 miles an hour, only 30 miles above the ice, deeper into the spray than it had ever dared. There was genuine risk in it. A thick enough jet, a large enough grain at that speed, could have damaged the spacecraft outright. But the reward was worth the gamble. Flying low and fast through the densest part of the eruption let the instruments gulp a far richer mouthful of the ocean's chemistry than any cautious distant pass ever could. Looking back, it reads almost like a rehearsal for the nerve the whole mission would need at the very end. A spacecraft willing to fly somewhere genuinely dangerous because the only way to learn what a hidden world was made of was to fly straight through its breath. What the plume contained is the reason this story exists. Most of it was water, plain water vapor and ice, around 98%. But laced through the water was everything else. Salt. Not a trace, but real salinity. The chemical signature of an ocean that has sat against rock long enough to dissolve it. Tiny grains of silica, the kind that on Earth only form when hot water pushes through rock at high temperature. Carbon dioxide, methane, ammonia, and organic molecules, the carbon-based building blocks that every living thing we have ever met is made of. One scientist described the brew coming off the moon as something like carbonated water with an essence of natural gas. It was, in other words, not the exhaust of a dead world. It was the breath of a chemically active one. The chemistry only grew richer as the team kept reading the grains. The ocean turned out to be mildly alkaline, what some scientists call a soda ocean, gentle rather than harsh, the kind of water that would not be hostile to life. Folded into the spray were not only simple carbon molecules, but large, complex organic compounds, heavy chains and rings of carbon, far bigger than anyone had expected to find leaking out of a small icy moon. These are the sort of molecules that, on Earth, sit a step or two below the machinery of life itself. Cassini was not just tasting water with a hint of carbon, it was tasting a sea brewing a genuinely complicated chemistry, the raw materials laid out and reacting, in the dark, beneath the ice. Piece by piece, across years of flybys, the team assembled a conclusion that none of them had gone looking for. The salt and the silica could not exist in the spray unless there was liquid water down there, real water, sloshing against a rocky floor and carrying its minerals up through the cracks. And it was not a small frozen pocket. When they measured the way the entire moon wobbles as it swings around Saturn, the wobble was too loose, too free for a solid ball. The ice shell was sliding on something. The only thing it could be sliding on was a global ocean, a sea of liquid saltwater wrapped around the whole core of the moon, sealed beneath miles of ice, kept warm by the same furnace heating the tiger stripes. Estimates put it as much as 6 miles deep in places. An entire hidden sea on a moon you could lose inside a single American state. The salt deserves a closer look because it was the real smoking gun. In 2009, a team led by the researcher Frank Postberg reported that the ice grains in Saturn's E-ring, the very grains Enceladus had flung into space, were rich in sodium salts, and pure ice, frozen straight out of vapor, would never carry salt like that. The only way to load those grains with sodium was for them to have frozen out of liquid salt water that had been sitting against rock long enough to dissolve its minerals, exactly the way the sea grows salty here on Earth. The salt riding in Saturn's outer ring was, in effect, a message smuggled out from the floor of a hidden ocean. And hold on to the name Postberg, because that same researcher would still be pulling secrets out of these grains many years later, long after the spacecraft that gathered them had ceased to exist. The reach of those plumes is hard to overstate. In one image taken in 2006, Cassini caught long, wispy fingers of bright, icy material, stretching thousands of miles out from Enceladus, threading into the E-ring like smoke caught in a slow current. And the eruptions were not just a scatter of separate jets. In places, the geysers lined up along the tiger stripes so densely that they merged into great curtains of spray, sheets of glowing mist hanging off the cracks for miles, lit from behind by the distant sun. A moon barely the size of a small country was throwing a veil of its own ocean clear across a region of space wider than the planet it orbits. Once you have seen that, the idea of a dead, quiet little ice ball never quite recovers. None of this landed in a single dramatic afternoon. It accumulated slowly across more than a decade, each result raising the stakes on the one before, the strange breathing of the magnetic field in 2005, the warm pole and the fountains the same year, the organic rich brew sampled in 2008, the confirmation, years later, that the ocean was not a trapped pocket but a globe-spanning sea. By the time the picture was whole, the people running Cassini understood they were no longer looking at a geological oddity. They were looking at one of the most promising places for life anyone had ever found, and they were looking at it through the exhaust of their own spacecraft. The moon was, in effect, handing us samples of its hidden ocean for free, flinging them into space where Cassini could fly through and read them, sparing us the impossible task of drilling through miles of ice. No one had to land. No one had to dig. The sea came up to meet us. Enceladus. Hold the name now, because from here on, it is the center of everything. Not Saturn, with its rings and its storms. Not Cassini, for all its years of faithful work. A 300-mile ball of ice that everyone had written off as a frozen pebble turned out to be hiding a warm, salty, mineral-rich ocean sealed in the dark, venting its contents into space through 4 cracks at the South Pole. We had spent decades searching the galaxy for the conditions that might allow life, and one of the most promising places we have ever found sat quietly in our own solar system, orbiting the planet we sent Cassini to study, spraying samples of its hidden sea directly into the path of our spacecraft. And that is precisely where the trouble began. Because once you know there is a sea down there, a sea with liquid water and organic chemistry and a source of heat, you have to ask the next question, and it is not a comfortable one. You have to ask whether anything lives in it. And the moment that question is on the table, a second question follows it like a shadow, one that has nothing to do with biology and everything to do with the machine that found it. Cassini was not clean. No spacecraft is. It had been built in rooms on Earth by human hands, and despite every precaution, it almost certainly carried hardy Earth microbes baked onto its surfaces, the kind of tough bacteria that can survive years of vacuum and radiation curled up in a dormant state. For 13 years, that had not mattered. But Cassini was running low on the fuel it used to steer. And a spacecraft that cannot steer cannot choose where it goes. Sooner or later, with its propellant gone, it would become a 5.5-ton projectile loose in a system that now contained a possible living ocean. Nobody could promise where it would drift. Nobody could promise what it might one day hit. And of all the places in that system, it must never, ever be allowed to fall. The very worst was the small white moon it had just proven might be alive. Before we follow the spacecraft to its grave, we have to sit with the discovery a little longer, because the case for Enceladus did not weaken under scrutiny. It got stronger and stranger. The closer the team looked, the harder it became to call that ocean merely interesting, and the easier it became to call it something far more loaded, possibly habitable. To see why that word carries so much weight, it helps to know what life actually requires, stripped down to its barest terms. When scientists ask whether a place could host living things, they are really asking 4 questions. Is there liquid water? Is there the right chemistry, the carbon-based building blocks that bodies are made from? Is there a source of energy, something a living thing could feed on? And has there been enough time for any of it to take hold? Liquid water, the right chemistry, an energy source, and time. Those are the conditions. Find all 4 together, and you have not found life. But you have found a place where life is not forbidden. Enceladus already had 2 of them outright. The ocean was liquid water beyond doubt. The plume was thick with organic chemistry, the carbon molecules every living thing relies on. Time, the 4th condition, the ocean almost certainly had as well, because the tidal heating that keeps it warm has been running for an enormous stretch of the moon's history, not a brief geological accident. That left a single open question, and it was the one that mattered most. Energy. Was there anything down there a living thing could eat? The first hint had been sitting in the data for years, in those tiny grains of silica. On Earth, grains of that exact size and kind form in one particular setting. Hydrothermal vents. These are places on the deep ocean floor where seawater seeps down into the hot rock, gets superheated, picks up dissolved minerals, and comes roaring back up through cracks as scalding, chemical-rich water. The silica in Enceladus's plume was the fingerprint of that process. It meant the moon's hidden sea was not sitting on cold, dead stone. It was in contact with hot rock, and hot water was circulating through that rock, somewhere down on the floor of a sea no light has ever touched. That matters because of what hydrothermal vents do here on our own planet. In the 1970s, when researchers first took submersibles down to the vents along the mid-ocean ridges, they found something nobody had predicted: life. Not scraps of it, but dense, thriving colonies. Tube worms taller than a person, blind crabs, mats of bacteria, whole ecosystems crowded around the hot chemical fountains, miles below the surface in total blackness, where not a single ray of sunlight has ever reached. Everything we had assumed about life turned out to be too narrow. These creatures did not run on sunlight, directly or indirectly. They ran on chemistry. The vents fed them, and they lived in the dark, completely independent of the sun. The trick those creatures use has a name: chemosynthesis. Almost everything you have ever seen alive runs, at the bottom of it, on sunlight. Plants catch it, animals eat the plants, and the whole web traces back to the sun. The vent communities broke that rule. At the base of their food web sit microbes that pull energy straight out of the chemicals streaming from the vents, building the sugars they need from the raw ingredients of hot mineral water. They turned chemistry into food without a single photon of light. And that is the thing that should make you sit up when you think about Enceladus, because a sealed ocean under miles of ice will never see sunlight. Not once, not ever. For most of the history of biology, that would have ruled it out completely. Chemosynthesis is the loophole. It means an ocean in permanent darkness is not automatically a dead one. That discovery rewired how we think about where life can exist. If life on Earth can cluster around chemical vents in the lightless deep, then sunlight is not the requirement we once thought it was. A buried ocean, sealed under ice, with hot vents on its floor, suddenly stops sounding impossible for life and starts sounding almost familiar. And many researchers suspect life on Earth itself may have gotten its start in exactly such a place, around vents like these, close to 4 billion years ago. To feel how long ago that is, understand that for nearly the entire history of our planet, long before there were forests or fish or breathable air, the only living things anywhere on Earth were microbes huddled in the dark around cracks in the ocean floor. The vents may not just support life, they may be where life began. Sit with what that implies for Enceladus, because it is almost vertiginous. If life on Earth began around hydrothermal vents in a dark ocean roughly 4 billion years ago, and if Enceladus has hydrothermal vents in a dark ocean right now, then that small moon may be running, at this very moment, the same opening experiment our own planet ran in its deepest past. Not a museum of how life might have started, a live version of it, ongoing, today, while you listen to this. We cannot watch the origin of life on Earth because it happened so long ago that the rocks that witnessed it are mostly gone, recycled away by the slow churn of our restless planet. But out at Saturn, there may be a sealed, undisturbed ocean quietly working through the very chemistry that became us, preserved in the cold, waiting. To study Enceladus might be to look back at our own beginning, happening somewhere else, all over again. So the team had a buried sea in contact with hot rock, with chemistry that looked uncannily like the cradle of life on Earth. There was one piece still missing, a clean, direct sign of available energy. And in the spring of 2017, flying through the plume one more time, Cassini found it. The instrument was the ion and neutral mass spectrometer, the same one that had been drinking the plume's gas for years. This time, the team ran it in a special mode, carefully tuned to rule out the hydrogen the spacecraft might produce on its own, so that anything left over had to be real. Anything left over had to have come from the moon. And there it was. Molecular hydrogen, streaming out of Enceladus in the plume, in real and measurable amounts. The finding was published in the journal Science by a team led by the researcher Hunter Waite, and it was the piece everyone had been waiting for. Here is why hydrogen mattered so much. When hot water reacts with certain rocks deep underground, it strips hydrogen loose and releases it, a process geologists have studied for decades. Finding hydrogen pouring out of Enceladus was direct evidence that this reaction is happening right now, on the floor of that ocean, hot water working against rock in the dark. But hydrogen is not only a sign of activity, it is food. On Earth, some of the most ancient microbes alive feed by combining hydrogen with carbon dioxide, and they get both energy and the carbon they need from that single reaction. They are called methanogens because the reaction's waste product is methane. And Enceladus had everything that reaction needs all at once. Hydrogen, freshly made at the vents. Carbon dioxide, measured in the plume. The chemistry of the ocean was tilted, out of balance, in exactly the direction that favors turning hydrogen and carbon dioxide into methane and energy. In plain terms, the ocean of Enceladus is not a still, finished, inert place. It is a chemical engine running out of equilibrium, with an energy gradient sitting right there, unused, the precise kind of gradient that life on Earth learned to feed on billions of years ago. The last of the four conditions had fallen into place. Liquid water, the right chemistry, an energy source, and time. Enceladus had all four. Researchers took the idea seriously enough to run the numbers on it. If methanogens, the hydrogen-eating microbes from Earth's deep places, were dropped into the conditions Cassini measured at Enceladus, could they survive? Could they grow? Several teams built models to ask exactly that, feeding in the temperatures, the chemistry, the available hydrogen, and asking whether a population could hold on. The models did not find a reason it was impossible. Some suggested that a real biosphere, if it existed, could sustain itself on the chemistry alone. None of this proves anything is there. A model is not a microbe. But it moved Enceladus out of the realm of pleasant speculation and into the short list of places in our own solar system where, by every measurable standard we know how to apply, life could actually make a living. Now sit with the timing of that announcement, because it is the strange knot at the center of this whole story. The hydrogen result, the single strongest piece of evidence that a small moon of Saturn might be able to support life, was made public in April of 2017. That very same month, Cassini began the final sequence that would end with its deliberate destruction. The discovery that Enceladus might be alive, and the decision to drive our spacecraft to its grave, did not happen years apart. They happened in the same few weeks. We confirmed the moon might hold life, and we condemned the machine that confirmed it, almost in the same breath. I want to be honest about the limits of what was found, because the honesty is part of what makes it powerful. Habitable does not mean inhabited. Everything Cassini measured tells us the ocean could, in principle, support living things. None of it tells us that anything is actually down there. We found the conditions for life, not life itself. There may be microbes thriving around those vents this very moment, an entire dark biosphere going about its business under the ice. Or there may be nothing at all, a perfectly habitable ocean that simply never got started. The genuine, unsatisfying, honest answer is that we do not know. And we built the next part of the story precisely because we do not know. Step back, though, and feel the size of what hangs on that uncertainty, because it reaches far past one moon. Suppose we did, one day, find life in the ocean of Enceladus, and suppose it turned out to be genuinely separate from ours, a second and independent beginning with its own chemistry, not some long-lost relative seeded back and forth on stray meteorites. That would rewrite our entire sense of where we stand. It would mean life began at least twice in this one ordinary solar system, on two different worlds by itself. And if life can start over twice around a single average star, then it is almost surely starting all over the place, on a quiet, uncountable number of worlds scattered through a galaxy of hundreds of billions of stars. To feel that number, try this. If you set out to count the stars in our galaxy alone, ticking off one every second without ever stopping to sleep, you would still be counting more than 10,000 years from now. A second, separate spark of life in our own backyard would whisper that the universe is not the empty, sterile place it can feel like on a cold, clear night. That is the true size of the question sealed under that ice. That is what we chose to keep clean. Because once you accept that Enceladus might be alive, the spacecraft situation changes completely. It is no longer just an aging explorer running low on gas. It is a contamination risk. And to understand why that single phrase was enough to sentence Cassini to death, you have to understand a quiet principle that has governed space exploration since the very beginning. It is called planetary protection. The idea is simple, and it cuts both ways. When we send a spacecraft to another world, we have an obligation not to carry our own life there with us. Partly, this is a matter of not wrecking something precious before we even understand it. If there is a native biosphere in the ocean of Enceladus, seeding it with hardy Earth bacteria could disrupt or destroy it. An alien invasion delivered by accident, and we would never even know what we had ruined. But there is a second reason, just as serious, and it is about not fooling ourselves. Imagine we return to Enceladus in 50 years, drill through the ice, sample the ocean, and find life. The discovery of the millennium. Except if our own spacecraft had crashed there decades earlier and spilled its microbes into the water, how could we ever be sure the life we found was native and not simply the descendants of stowaways we delivered ourselves? We would have contaminated the experiment before we ran it. The answer would be forever unknowable. This principle is older than Cassini, and we have acted on it before. It reaches back to the dawn of the space age, written into the Outer Space Treaty of 1967, which binds spacefaring nations to avoid the harmful contamination of other worlds. An international committee sorts every mission into categories based on where it is headed and how likely that destination is to harbor life, and the rules tighten the closer you get to a place that might be living. When NASA sent the 2 Viking landers to Mars in the 1970s, it baked them in great ovens before launch, roasting them for hours to kill anything that might be clinging to them. Sterilization by heat before the journey even began. And there was a direct precedent for exactly what Cassini would do. In 2003, NASA deliberately flew its Galileo spacecraft, the great explorer of Jupiter, straight into that planet to destroy it, for precisely the same reason we are talking about now. Galileo had found strong evidence of a buried ocean inside Jupiter's moon Europa, And rather than risk a dead, drifting spacecraft one day crashing into Europa and seeding it with Earth life, NASA chose to burn Galileo in the clouds of Jupiter instead. So Cassini's ending was not a strange one-off act. It was the second time we had deliberately killed one of our own great explorers to protect a possibly living moon. Given what we keep finding out there, it will not be the last. We are slowly becoming a civilization that builds a thing, sends it to look, and then destroys it on purpose to keep from spoiling what it sees. And Earth life is alarmingly good at hitching a ride. Spacecraft are assembled in clean rooms, scrubbed and sterilized as thoroughly as we know how. But no cleaning is perfect. Certain microbes form tough, dormant spores that can shrug off the things that should kill them. There are organisms that survive years of hard vacuum, that endure radiation doses that would destroy us many times over, that lie frozen and inert for decades, and then revive when conditions turn favorable. We have names for some of them. There is a bacterium called Deinococcus radiodurans, hardy enough to survive radiation hundreds of times the dose that would kill a person, which earned it the nickname Conan the bacterium. There are tardigrades, the microscopic animals that have been exposed to the raw vacuum of space on the outside of a spacecraft and come back alive. There are bacterial spores pulled from places on Earth so harsh that nothing should grow there at all. Life does not give up easily, and the toughest of it is exactly the kind most likely to survive a long cold ride to Saturn. Some have been carried to the outside of the space station and brought back still viable. A spacecraft is not a sterile object. It is, in the worst case, a vessel carrying a few resilient Earth organisms in suspended animation, waiting for warmth and water. And Enceladus is nothing but warmth and water under that ice. And it would not take an invasion to ruin it. That is what makes planetary protection so unforgiving. A single surviving microbe, one resilient spore that woke in that warm water and found it agreeable, could in principle multiply, spread, and over enough time turn a pristine alien ocean into a distant branch of Earth's own biosphere. There is no taking that back. You cannot recall a contamination. You cannot sterilize an ocean once something living has been loosed inside it. The asymmetry is total and merciless. We might gain a little science by gambling with it, but if the gamble went wrong, we would lose the thing itself, permanently, along with any hope of ever learning what was genuinely there to begin with. When the stakes are shaped like that, where one bad outcome is forever and cannot be undone, caution stops being timidity and becomes the only sane move left on the board. This is where the fuel comes back into the story. Cassini steered itself with small thrusters that burned a limited supply of propellant, and after 20 years and countless maneuvers, that supply was nearly gone. A spacecraft with no propellant is a spacecraft that can no longer choose where it goes. Its orbit becomes the plaything of every gravitational nudge from every passing moon, drifting and bending over years and decades in ways no one can fully predict. Leave a dead, uncontrolled, possibly contaminated spacecraft looping through the Saturn system for the next few centuries, and sooner or later, the odds catch up with you. One day, its wandering path could intersect Enceladus or Titan, and a piece of Earth would crash into a world that might be alive. This is what surprises people most. The decision to end Cassini this way was not made in a panic at the last minute. It was made years in advance, with cold deliberation. Back in 2010, when the mission was granted its final long extension, the plan for that chapter was written with the ending already built in. The spacecraft would spend the rest of its working life exploring, and it would spend the very last of its fuel steering itself into Saturn on purpose. The people running the mission knew, 7 years before it happened, roughly when and how their spacecraft would die. They flew it for 7 more years of brilliant science, with that ending already waiting at the bottom of the schedule, like a date circled on a calendar nobody wanted to reach. The fuel in question was the propellant the spacecraft burned to steer, and there was no way to make more of it or send any out. Every turn the spacecraft had ever made, every careful nudge to line up a flyby or point an instrument, had spent a little of a tank that started full at launch and could only ever go down. By the final years, the engineers were watching the gauge the way you watch the needle on a long drive through empty country with no station for miles. And the danger of running dry was not that Cassini would simply stop. It was that it would keep going blindly. A spacecraft with empty tanks still moves, still loops around Saturn, but it can no longer correct its path. Every close pass of a moon tugs that path a little, and those tugs add up across decades and centuries into something genuinely chaotic, impossible to predict and impossible to steer away from. Run the clock far enough forward, and an abandoned Cassini could end up almost anywhere in the system, including the 2 places it must never go. So the team looked hard for another way out, and one by one the alternatives failed. They could try to park Cassini in some distant orbit and hope it stayed put, but nothing that far out stays put for long, not with so many moons tugging at it across the centuries. They could try to fling it clear of Saturn entirely, out into deep space the way Voyager left the Sun behind, but that takes a hard shove of propellant, and the propellant was exactly what they no longer had. They could simply switch it off and walk away, leaving it to drift, but that was the one outcome planetary protection could not allow, because drifting is precisely the danger. Every safe-sounding option carried the same flaw. None of them could guarantee, with certainty, that this machine would never touch the moon it had discovered. Only one option could make that guarantee. Drive Cassini straight into Saturn deliberately, while there was still enough fuel left to aim it. Send it down into the crushing pressure and searing heat of the giant planet's atmosphere, where it would not crash and scatter, but burn, breaking apart and vaporizing completely. Every component, every surface, every last dormant microbe destroyed by friction and heat in a matter of seconds. Total sterilization by fire. A spacecraft that no longer exists cannot contaminate anything. It was brutal, and it was final, and it was the only path that removed the risk entirely. So that is what they chose. Years in advance, the people who had spent their careers flying Cassini sat down and planned the precise hour at which they would aim their healthy, irreplaceable $3.5 billion spacecraft into a planet and let it burn. They did it not because the mission had failed, but because it had succeeded too well. It had found Enceladus. It had found the ocean, the vents, the hydrogen, the 4 conditions stacked one atop another. And the discovery was so important, the possibility of life so real, that protecting it mattered more than the spacecraft that made it possible. The machine we built to look for life was, in the end, killed by the very thing it found. Hold on to the size of what was given up. Cassini cost something on the order of $3.5 billion to build and fly. It was the work of thousands of people across more than 24 countries, the product of careers that began when the people running it were young and ended with their hair gone grey. For many of the scientists and engineers, this spacecraft had been the center of their professional lives for the better part of 3 decades. They had grown up with it, in a sense, and they were the ones who had to plan, in careful detail, exactly how to destroy it. They spoke about it the way you might speak about a hard decision made for someone you love. There was no failure to blame, no malfunction to point to. The spacecraft had done nothing wrong. It had, if anything, done too much right. And still the choice was clear to them, and they made it without flinching, because the principle underneath it was one they believed in. You do not gamble with a world that might hold life to spare a machine, no matter how much that machine means to you. The mission would end not with a slow fade of dying power, but with a deliberate, useful death aimed squarely at protecting the very thing it had discovered. There is something almost unbearably human in that. We built a tool. The tool found something that felt sacred, and so we chose to give up the tool to keep the sacred thing safe. There is a hard kind of grace in that decision, and we should not rush past it. But the choice also opens onto something larger, something about us, about what kind of explorers we are willing to be when no one is watching, and the thing we are protecting may not even exist. That is where this has to go next. The mechanism is interesting. The implication is something else entirely. Because step back from the engineering for a moment and look at what kind of decision this really was, and you find a portrait of us that we almost never get to see. We are not, as a species, known for restraint. Our history is a long story of arrival and taking. We have crossed every ocean and climbed into every valley, and almost everywhere we have gone, we have brought our weeds, our rats, our diseases, our hunger, reshaping or erasing whatever was there before us, usually without meaning to, and often without even noticing, until it was gone. That is the pattern. We expand. We touch everything. We rarely leave a place the way we found it. And then, out at Saturn, faced with a small moon that might be cradling the second example of life ever discovered, we did the opposite. We drew a line and chose not to touch it. We took the single most valuable machine we had ever sent to the outer solar system, and we destroyed it on purpose to make certain we could not contaminate a sea we may never even reach. As far as I can tell, that is one of the first times in our entire history that we have looked at a possibly living world and decided in advance and at real cost to protect it from ourselves. Not because a law forced us, not because anyone was watching, because it was the right thing to do, and the people in charge believed that quietly enough to act on it. There is something in that I find genuinely moving and a little hopeful, in a way that has nothing to do with Saturn. It suggests we are capable of restraint at a distance, capable of valuing the bare possibility of life over our own hardware and our own curiosity. We sacrifice the thing we loved to keep clean a place we might not visit again for a generation. That is not the behavior of a species that only takes. It is maybe a glimpse of the kind of explorers we could choose to be. Set the two endings side by side, and the difference is the whole point. The Voyager probes, the ones we met at the start, will get the ordinary fate, the slow fade, the drift. Two silent machines coasting between the stars for millions of years with no one to mark the moment they finally go dark. There is a loneliness in that, but also a kind of immortality. Cassini got the opposite, a death with a date, a purpose, and a target. It did not get to drift on as a frozen monument to itself. It got to mean something with its ending, to spend its last breath protecting the very thing that made its life worthwhile. I am not sure which ending I would choose, if a machine could choose. But there is something in Cassini's that feels less like an extinction and more like a sacrifice. And the difference between those two words is the difference between merely stopping and choosing to stop for a reason. Now bring back the 83 minutes, because here is where that number stops being a piece of trivia and turns into something heavier. Saturn is so far away that no one on Earth could fly Cassini in real time during its final dive. We have touched on this already, but on the last day, it became the whole shape of the event. A command sent from Earth took well over an hour to arrive. A report of what the spacecraft had done took just as long to come back, so the plunge could not be flown by hand, watched and adjusted as it happened. It had to be loaded into the spacecraft's memory ahead of time, a sequence of instructions Cassini would carry out alone in the dark, with no one able to reach across the gap and change a thing. By the time any human being saw a single bite of what was happening, it had already happened 83 minutes in the past. The decision had to be final long before we would ever know it was done. Think about what that means. We could not save it even if we changed our minds. There was no red button to slam at the last second, no chance to shout stop. Whatever Cassini did on the way down, it did completely on its own, following orders written weeks earlier by people who would then have to sit in a room and wait, helpless, for the light to crawl across the solar system and tell them what had already become of their spacecraft. They were not going to witness the death. They were going to receive it, like a letter from someone already gone. But before the end came 5 of the strangest, boldest months of the entire mission. They called it the grand finale, and it began with a goodbye. On the 22nd of April, 2017, Cassini made one last close pass of Titan. The mission team called it the goodbye kiss because Titan's gravity was about to be used one final time, not to steer the spacecraft toward more science in the ordinary way, but to bend its path into the shape of its own ending. That single flyby reshaped the orbit so that Cassini would leap up over the icy rings and come diving down through a narrow gap between the innermost ring and the cloud tops of Saturn itself. A gap only about 1,200 miles wide. A region no spacecraft ever had flown through. 4 days later, on the 26th of April, Cassini took its first dive through that gap. And then it did it again and again, once a week for 5 months. 22 times in all, each pass threading the same impossibly narrow lane between the planet and its rings at more than 75,000 miles an hour. It was, in every meaningful sense, a brand new mission flown by an old spacecraft, exploring a place we had circled for 13 years and never once been able to reach. And here is the quiet irony that sits underneath the grand finale. Those dives were wildly risky. Flying through a gap beside the rings at that speed, even a stray ice chip the size of a grain of sand could have punched through the spacecraft and ended everything. For 13 years, the team would never have dared it. The spacecraft was too precious, the risk too high. But now Cassini was already sentenced to die. There was nothing left to protect. And that freedom, the strange liberty of a machine with nothing left to lose, unlocked the most daring science of the entire mission. The death sentence is what set the spacecraft free to go where it never could have gone, while we were still trying to keep it alive. What it found in that gap rewrote pieces of the textbook. The region turned out to be startlingly empty, far cleaner of dust than anyone had predicted. So quiet the engineers had armored the spacecraft against debris that mostly was not there. Cassini measured the pull of the rings and the planet so precisely that it could finally weigh the rings themselves, and the answer was a small shock. The rings are light, and light rings are young rings. The math suggested Saturn's glorious rings may be no more than 100 million years old, maybe far less, which means that when dinosaurs walked the Earth, Saturn might have worn no rings at all, or a very different set. The most famous rings in the solar system may be a recent and temporary ornament, and we happen to be alive at the brief moment they exist. And they may not stay. Among the things those dives measured was that slow rain of ring material falling steadily down into Saturn, a constant drizzle of ice and dust pulled out of the rings and into the planet's atmosphere below. At the rate Cassini clocked, the rings are draining away, and on a cosmic clock they are draining quickly, perhaps gone in another 100 million years. Put the two findings together, and they say something quietly staggering. The rings are young, and the rings are dying. They were most likely not there when the dinosaurs walked, and they will most likely be gone long before the sun does. We happen to exist in the narrow window when Saturn wears its halo at all, and we happen to build a spacecraft just in time to fly through it before it fades. There is a strange luck in that, a sense of having shown up at precisely the right moment to witness something that will not always be there to see. The dives measured more. By feeling the planet's gravity and its magnetic field from closer than ever before, Cassini probed the inside of Saturn, finding deep winds running thousands of miles down and a strange, fuzzy, not quite solid core. It pinned down something as basic as the length of a day on Saturn, a number that had stubbornly resisted measurement for decades, settling it at around 10.5 hours. Every dive brought the spacecraft a little lower, walking its orbit inward week by week until the 20-second pass was no longer a pass at all. The 22nd time, Cassini did not come back up. So here is how the last day actually unfolded. On September 14th, 2017, Cassini took one last long look around. It turned its instruments on Saturn and its moons and gathered a final set of observations, including its last images, the closing entries in a photo album 13 years deep. Then it did something quietly devastating. It pivoted its big dish antenna toward Earth and locked on, and it held that lock. Because from this moment until the very end, it would be talking to us continuously, sending everything it could for as long as it possibly could. It pointed itself home, and it started its goodbye. The next morning, the plunge began. Cassini was falling towards Saturn now at tremendous speed, somewhere around 70,000 miles an hour, fast enough to cross the entire United States in about 3 minutes. It rolled itself slowly to aim a particular instrument, a device for sniffing the chemistry of the atmosphere, straight into the gas it was about to enter. This was the whole point of the final descent. The spacecraft was not simply dying. It was working, harder than ever, reaching into a place no probe had ever gone and reading it directly, sending the numbers home in close to real time. And this is the answer to the question we opened with. What did Cassini send home just before it burned up? Science. Real, irreplaceable science. 8 of its instruments were switched on during the plunge, sampling the upper atmosphere of Saturn, measuring the magnetic field, the plasma, the temperature, the actual composition of the gas, deeper into the planet than any instrument had ever reached. Its very last act was to taste a world from the inside and describe it to us as it fell. Most of us, when we die, are simply gone. Cassini spent its final minutes narrating the inside of a planet to the people who built it, and the data it sent in those last moments is still being studied today. Those final readings were not a sentimental gesture. They were measurements no one had ever been able to take. For 13 years, Cassini had studied Saturn from a safe distance, always above the clouds, always inferring what lay deeper. On the way down, it finally reached in and read the upper atmosphere directly, sampling the gas itself, the behavior of the planet's magnetic field down low, the exact mix of elements at a depth no instrument had ever touched. That data has been feeding our models of how Saturn is built ever since, helping settle long arguments about the planet's deep interior, its winds, and how much heavy material it hides inside. A spacecraft cannot ask for a better death than to spend it gathering numbers nobody else could reach. Cassini did not simply die well. It died working, and the work outlived it. Then the atmosphere began to bite. As Cassini sank into the thickening gas, the friction tried to spin it, to tumble it, to wrench its antenna off the line to Earth. The spacecraft fought back the only way it could. Its small thrusters, the same ones that had steered it for 20 years, began firing to hold it steady, to keep that dish locked on the distant point of light that was home. They started gently, at 1/10 of their power. As the gas grew thicker, the strain climbed, and the thrusters worked harder and harder, ramping up over the span of about a minute until they were firing at full strength. Everything they had, just to keep the antenna pointed at us for a few seconds more. It was not enough. It was never going to be enough. The moment came, roughly 900 miles above the cloud tops, when the atmosphere finally overpowered the thrusters and Cassini could no longer hold its aim. The antenna slipped off Earth. The signal cut. In the seconds after that, the spacecraft tumbled, came apart, and burned, breaking up like a meteor and vaporizing into the sky of the planet it had studied for 13 years. From the first bite of atmosphere to the final silence, it lasted about 91 seconds. It held itself together and kept talking almost to the last, tumbling only in the final 8 seconds before the end. And 83 minutes later, in a control room in California, the line went quiet. The signal that confirmed the end reached Earth at 55 minutes and 46 seconds past 11, coordinated universal time, on the morning of September 15th, gathered in by a giant dish antenna in the Australian outback. The spacecraft held on about 40 seconds longer than the engineers had predicted, a last small stubbornness. And then the thin trace of its signal flattened into noise, and the project manager, a man named Earl Mays, told the room simply that this was the end of the mission. People who had given decades of their lives to this machine stood at their consoles and wept and embraced and stared at screens that had just gone flat. And they were not alone in watching. All over the world, people had set alarms for the small hours of the morning to be awake for it. They gathered in planetariums and lecture halls and living rooms, watching the feed from that control room in California, waiting for a thin line on a graph to flatten. It is a strange thing to grieve a machine, but this one had sent home postcards for a generation, had become, for a lot of people, the friendly face of the whole adventure of exploring the outer solar system. When the signal died, people who had never touched the spacecraft, who lived nowhere near it, felt the loss in their chests. We had, without quite meaning to, fallen in love with a robot 1 billion miles away, and we stayed up to be with it at the end. But here is what I cannot stop turning over. Everyone in that room was grieving something that had already finished. By the time the signal arrived to tell them Cassini was gone, the spacecraft had been gone for 83 minutes. While they sat there in the last tense moments, watching the trace, waiting, hoping it would hold on a little longer, there was nothing left to hold on. Cassini was already part of Saturn. It had already burned, already scattered, already ended, more than an hour before. They were watching a ghost. The light just had not finished arriving yet. That gap, that 83 minutes, is not a quirk of one spacecraft's death. It is the condition of everything we see in the sky. Light is fast, the fastest thing there is, quick enough to circle the entire Earth more than 7 times in a single second. And even light needed an hour and 23 minutes to cross the nearly billion miles between Saturn and home. The universe is so large that its speed limit becomes a kind of delay built into reality. We never see the cosmos as it is. We only ever see it as it was, by the time its light reaches us. Cassini's death simply made that truth small enough, and close enough, and human enough to break your heart over. There is a lesson folded into that delay, if you want one, and it is not a sad lesson. We spend our whole lives reaching for things across distances, in space and in time, and so much of what we love we only ever know at a remove after the fact, by the light it left behind. A letter, an old photograph, a voice on a recording. The 83 minutes is only the cosmic version of something we already live with every day. We are always a little late to the things we cherish, always receiving them, rather than gripping them in the very instant they happen. And yet the feeling lands anyway. The grief in that control room was real, even though the thing it mourned had already been gone for over an hour. The light still arrived. The message still came. Distance does not erase what reaches us. It only makes us wait for it. And the waiting, it turns out, is most of what love across a great distance has always been. And here is something that still raises the hair on my arms. Cassini kept making discoveries after it was dead. The spacecraft burned up in 2017, but the mountain of data it had gathered did not burn with it. It sat in archives, and scientists kept sifting through it year after year. In 2023, 6 years after the spacecraft was gone, a team led by that same researcher, Frank Postberg, found something in the old records that no one had noticed before. Phosphorus, locked inside the Enceladus ice grains in the form of phosphates, at concentrations many times higher than in our own oceans. Phosphorus is one of the 6 elements that every living thing on Earth is built from, the rarest of them, the hardest to find, and the last one still missing from the checklist for Enceladus. With that single discovery, the little moon became the only place beyond Earth where we have detected all 6 of life's essential ingredients together in one body of water. A spacecraft that had been scattered ash in Saturn's atmosphere for 6 years reached back through its own archived data and handed us the final piece of the puzzle. It was still discovering things long after it had stopped existing. The dead can still speak if they left enough behind. And what did all of it buy? Here is the honest, uncomfortable answer. It brought a question, not an answer. A question kept clean. We still do not know if anything lives in the ocean of Enceladus. We never found out. We found the water, the heat, the chemistry, the energy, every box on the checklist ticked, and then We deliberately destroyed the only spacecraft in position to keep looking, precisely so that one day, when we go back, we can ask the question properly, with no chance that the answer is just our own microbes staring back at us. There is no funded mission flying there now. The next close look at that ocean is years away at best, maybe decades, waiting on budgets and rockets and the slow patience of a species that thinks in quarters while the cosmos thinks in eons. For now, Enceladus keeps its secret, and we chose on purpose to let it. That does not mean we have given up the search. Far from it. In October of 2024, NASA launched a large spacecraft called Europa Clipper toward Jupiter's moon Europa, another world with a buried ocean sealed under ice, on a mission built specifically to learn whether that ocean could support life. It will reach the Jupiter system in the early 2030s and loop around the giant planet, sweeping past Europa again and again, doing for that moon something close to what we may one day do for Enceladus. There are also serious proposals on the table for going back to Enceladus itself. Mission concepts for a craft that would orbit the moon, fly through the plume again with far better instruments, and perhaps even land at the South Pole to taste the spray directly and search it for the signature of life. None of those are flying yet. But the point is that we are still going to ocean worlds, still asking the question, simply asking it cleanly, in a way our own fingerprints will never be able to spoil. Enceladus will get its turn. The patience is the whole point. That is the strange weight Enceladus carries by the end of this story. It started as a footnote, a small frozen moon nobody expected anything from. It became the most promising address for life in the solar system. And then it became the reason we destroyed our own spacecraft, the thing we valued so highly that we would give up almost anything to keep from spoiling it. A 300-mile ball of ice, holding a hidden sea, holding a question we were willing to kill for in order to protect. We did not save Cassini. We saved the possibility that Enceladus might still have something to tell us someday, in its own time. And yet, even now, even after all of it, the deepest question simply sits there, unanswered, under all that ice. We protected the ocean. We did not learn its secret. Everything this story can give you stops at the edge of that water. And the one thing we most want to know, whether we are alone or whether something small and patient is living in the dark down there, remains exactly as unknown as it was before Cassini ever launched. We bought ourselves the right to find out cleanly. We did not buy the answer. The answer is still down there, waiting, in a sea we chose not to touch. Most tellings of this story stop at Enceladus, the moon, the ocean, the noble death. There is a deeper layer, and it doubles the weight of everything we have said, because Enceladus was not the only world Cassini died to protect. There were two. The second one is the largest moon Saturn has, and in some ways, it is the strangest place Cassini ever touched. Its name is Titan. Titan is enormous for a moon. It is bigger than the planet Mercury, a genuine world in its own right, and it is the only moon in the entire solar system wrapped in a thick atmosphere. That atmosphere is the problem and the wonder of it, a dense orange smog so opaque that for centuries Titan was just a fuzzy amber dot, a world with its face permanently hidden behind a veil. We could see that something was there. We could not see the surface. Whatever Titan was doing under that haze, it did in private. Lifting that veil is what the Huygens lander was built for. and the way it did so remains one of the boldest things our species has ever pulled off. Remember that Huygens had ridden bolted to Cassini's flank for 7 years, asleep all the way from Earth. On the 14th of January 2005, it fell into Titan's atmosphere and began the most distant landing humanity has ever attempted, on a surface no one had ever laid eyes on, 1 billion miles from the nearest person who could help if anything went wrong. For 2 hours and 27 minutes, it drifted down through the orange haze under its parachutes, and as it fell, its cameras and instruments drank in everything they could. And what came back up the link, relayed through Cassini and across the solar system to Earth, stopped people cold. Because Titan, this frozen alien moon at the edge of the cold, looked uncannily like home. Huygens saw drainage channels cut into hillsides, the unmistakable branching pattern of rivers. It saw what looked like a coastline, a boundary between rough, bright highlands and a darker, flatter plain, as though it were drifting in over a shore. And when it finally touched down, softly, on a damp, dark surface with the give of wet sand, the view around it was littered with rounded pebbles, smoothed and tumbled as if they had spent a long time rolling in a streambed. It even recorded the faint sound of wind moving across an alien world, the first sound ever heard from the surface of another planet's moon. Then, it kept transmitting for another 72 minutes from the ground before the cold and the dark took it. The way it landed told its own quiet story. Huygens did not slam down or bounce. The instruments recorded the touchdown as a gentle crunch, the probe punching through a thin, brittle crust and settling into something soft beneath. The texture, one scientist offered, of creme brulee, a firm skin over a softer layer. Around it lay a damp plain scattered with those rounded stones, and the stones were not rock in any sense we would recognize. They were lumps of water ice, frozen so hard at that brutal cold that they behaved like river rocks, tumbled smooth by liquid methane that had flowed there once and might flow again. A pebble-strewn riverbed under an orange sky, on a moon 1 billion miles away, photographed for 72 minutes by a machine that had slept for 7 years to get there. Then silence. Rivers, shorelines, rounded stones, rain-carved hills, on a moon nearly 1 billion miles from the sun. But none of it is what it looks like. And that is where Titan becomes genuinely uncanny. On Titan, it is far too cold for liquid water. The surface sits at around 290 degrees below 0 Fahrenheit. At that temperature, water is not a liquid at all. It is rock. The ice on Titan is so cold it behaves like stone, and it forms the bedrock, the hills, the very ground Huygens landed on. The water on Titan is the mountains. So what carved the rivers? What fills the lakes? What falls as rain? Methane, and its cousin, ethane. The same hydrocarbons we burn for fuel here, the stuff of natural gas, which on Earth we only ever meet as gases unless we pressurize them in a tank. Titan is so cold that methane and ethane flow as liquids, the way water flows here. And so Titan runs a complete weather cycle, a full water cycle in every respect except that the water is not water. Methane evaporates from the lakes, rises, gathers into clouds, and falls again as rain, fat, slow drops of liquid methane drifting down through the thick air. The rain feeds rivers of methane that carve the hills and run down to seas of methane, standing dark and still at the poles. There is a place out there where it rains gasoline from an orange sky onto a ground made of frozen water, and the rain runs downhill into seas. That is Titan, It is the most Earth-like place we have ever found, built entirely from the wrong materials. Some details of Titan's weather sound made up. Because the air is so thick and the gravity so gentle, methane raindrops there do not fall the way ours do. They grow fat, as wide across as marbles, and they drift down slowly, almost lazily, taking their time through the heavy orange air, a rain so unhurried you could nearly follow a single drop from cloud to ground. And beneath all of it, sealed under the icy crust the same way Enceladus hides its sea, Cassini found evidence that Titan too holds a buried ocean of liquid water, salty and deep, locked far below the methane lakes on the surface. So Titan stacks two alien worlds into a single moon, a frigid hydrocarbon world of methane rain and mirror-flat seas on the outside, and a dark water ocean hidden underneath. And either one of them might, in its own utterly different way, have something to teach us about how a world becomes alive. Two oceans, on two moons, both uncovered by the same spacecraft, both placed forever off limits by its death. Cassini mapped those seas from orbit, peering through the haze with radar, the way a doctor sees through flesh. It found great bodies of liquid clustered near the North Pole, true seas, large enough that we gave them names. Kraken Mare, the biggest, broad enough to swallow one of Earth's Great Lakes. Legia Mare beside it. Smaller lakes scattered across the polar terrain, and one lonely lake, Ontario Lacus, down in the south. On its final close pass of Titan, the same goodbye kiss that bent it toward its death, Cassini sounded some of those northern lakes with radar and found them startlingly deep, more than 300 feet in places, brimming with liquid methane. The seas lie so flat and so calm that the waves on them rise barely a fraction of an inch. Standing on that shore, you would see a perfect black mirror stretching to the horizon under a hazy orange sky, utterly still, unimaginably cold. And there is so much of it. Titan holds more liquid hydrocarbon on its surface than all the oil and natural gas reserves on Earth combined many times over. Along its equator stretch vast fields of dark dunes, hundreds of feet tall, made not of sand but of fine grains of organic material, carbon-rich particles drifting down out of the sky and piling into great wind-sculpted ridges that run for hundreds of miles. There is more organic matter sitting in Titan's dunes than in all the coal beds of Earth. This is a moon drenched in the raw chemistry of life, soaked in carbon compounds, with liquid flowing across its surface, and an atmosphere thick enough to walk around in. The only thing missing is the warmth. Try standing there, the way we stood on Enceladus a little while ago. Titan is the one alien world where you could, in a sense, move around almost comfortably if you bundled up hard against the cold and carried your own air. The atmosphere is thicker than Earth's, dense enough that you would feel it press against you like deep water, and the gravity is so light that you could strap a pair of wings to your arms and genuinely fly, flapping slowly through the heavy orange air like a great clumsy bird. Above you hangs a hazy amber sky, the sun no more than a small bright smudge behind the smog. Around you, dark dunes of organic sand run to the horizon in long-combed ridges. Somewhere past them lies a shoreline, and beyond that, a black sea so still it holds the dim sky in like polished glass. It is one of the very few places out there that is not simply killing rock or lethal radiation, but a real world with terrain, weather, seasons, and shores. Strange past all reckoning, and yet in its bones, eerily like a frozen sketch of home. So the obvious question arrives: the same one Enceladus raised. Could anything live there? And Titan offers not one answer, but two. The first is the conventional one. Cassini found evidence, hidden in the way Titan flexes under Saturn's pull, that beneath the icy crust there is very likely a buried ocean of liquid water, salty and dark, much like the one inside Enceladus. By that measure, Titan is a second ocean world, another sealed sea that might, in principle, hold life of a familiar kind. But there is a second, wilder possibility, and it lives on the surface, in the methane itself. A handful of scientists have asked whether life could arise that uses liquid methane as its solvent instead of water, a biochemistry built on entirely different rules, life that would find our warm, wet world as lethal as we would find its frozen lakes. It is deep speculation. No one has found a trace of it, but Titan is the one place we know where the question is not absurd. And we are going back to Titan sooner than you might expect. NASA has built a mission unlike anything that has flown before, a nuclear-powered flying machine called Dragonfly. It is a rotorcraft, an 8-bladed drone about the size of a car, designed to do something never once attempted anywhere beyond Earth. It will fly. Titan's air is thick and its gravity is gentle, which makes it, of all the strange places in the solar system, the single easiest world on which to fly an aircraft. Dragonfly is set to launch in 2028 and arrive at Titan around 2034, where it will lift off and soar from one site to the next across the dune fields, landing, sampling the ground, and flying onward, the first aircraft ever to take to the skies of another world. What Dragonfly is hunting for is the chemistry of life's beginnings. And that is the other reason Titan grips us so hard. Its thick orange haze is built from complex carbon molecules called tholins, exactly the kind of rich, messy, organic chemistry that may have blanketed the early Earth before life ever stirred. Titan is, in a real sense, a frozen laboratory running the opening experiments of biology in extreme slow motion, the chemistry that comes before life, paused and preserved in the deep cold for us to read at our leisure. And there is so much of it still unmapped. A bright highland the size of the continent of Australia, named Xanadu, sits near the equator, its surface cut by channels that look carved by ancient methane rivers, a whole continent we have barely begun to understand. Cassini swung open the door on every bit of this. Dragonfly is how we finally walk through it. And notice the shape of that. Cassini found these worlds, and then it died to keep them clean. Dragonfly and the ocean world missions coming behind it are the reason that sacrifice was not wasted. We did not protect Enceladus and Titan in order to forget about them. We protected them so that the next machines, carrying sharper instruments and cleaner hands, could go and ask the real question one day without spoiling the answer in advance. There is a kind of relay being run here across the decades, each spacecraft handing the work to the next, each one a little wiser about how to look at a world without harming the thing it came to see. Cassini ran its leg of that race for 20 years, and then it stepped aside in the only way left to it, by taking itself off the board completely. The machines that follow will stand on what it learned, and on what it chose not to touch. That is what a good death buys, out here at the edge of the cold. Not an ending, a clean place for someone else to begin. Which means Titan 2 was a world we could not risk contaminating, a possible buried ocean, a surface that might, just might, host a chemistry of its own. When NASA weighed where a dead, drifting Cassini might one day crash, Titan sat on the forbidden list right alongside Enceladus. The spacecraft was not destroyed to protect a single moon. It was destroyed to protect two of them, two separate experiments in how a world can be alive, both of which Cassini itself had revealed to us. The more it discovered, the more places there were that it could no longer be allowed to touch. Its own success is what sealed its fate. And notice what this does to the question on the thumbnail, the question we started with. What did Cassini send home just before it burned up? We answered it once already, with the atmosphere data from the final plunge. But the fuller answer reaches back across the whole mission. Among the last great gifts it sent home were those radar soundings of Titan's deep methane lakes taken on its final pass, the goodbye kiss. And the images Huygens captured on Titan's surface remain, to this day, the most distant photographs ever taken from the ground of another world. We have never landed anywhere farther. Cassini's legacy of what it sent home is not one last transmission. It is a library, and the final entries were written on the way to the grave. There is one more piece to this, and it is the most human part of the whole story. It has nothing to do with oceans or moons. It has to do with how Cassini almost never flew at all. Remember the plutonium. Saturn is too far from the Sun for solar panels to be of any use, so Cassini, like the deep space probes before it, carried a nuclear power source, about 70 pounds of plutonium, whose slow radioactive decay gave off heat that the spacecraft turned into electricity. That is what kept it alive for 20 years. But in the years before launch, that plutonium became the center of a bitter fight. People were afraid. They imagined the rocket exploding on the pad or falling back to Earth, scattering radioactive material across Florida and beyond. Thousands of protesters gathered. The environmental reviews ran to thousands of pages. There were lawsuits and petitions and real public anguish, a serious national argument about whether it was worth the risk to launch this thing at all. To many people at the time, Cassini was not a noble explorer. It was a flying hazard, a contamination risk pointed at their own backyard. Hold those two moments side by side, because the symmetry is almost too perfect to be real. At the beginning, Cassini was feared as a thing that might poison the Earth. At the end, Cassini was destroyed to make certain it could never poison anything else. The machine that launched under protests about contamination spent its final breath as the most scrupulous act of contamination control we have ever performed beyond our own planet. The thing once seen as the danger became the guardian. The spacecraft people did not want to let off the ground gave its life, decades later, to protect two alien oceans from the touch of Earth. I do not know a cleaner illustration of how completely the meaning of a thing can turn, given enough time and enough distance. So when you weigh what Cassini was, hold all of it at once. The launch that almost did not happen, the 7-year fall through the inner solar system, the 13 years of postcards, and the 2 living possibilities it uncovered and then chose to shield with its own destruction. Cassini did not die for one ocean. It died for 2 ways a world can be alive. One running on water and one running on something we barely have a name for. Both of them kept safe, for now, by the deliberate end of the machine that found them. So come back, one last time, to the question we started with. What if the most important thing a machine ever did was choose to die? We can answer it now. Cassini chose to die so that a moon might keep its secret a little longer, untouched by us. It is the rarest kind of ending. Not a failure, not an accident, not a slow fading out. A death with a purpose, aimed like an arrow at the one thing worth protecting. And the strangest detail of all, the 83 minutes, turns out not to be strange at all. It only feels that way because it happened to a thing we loved. But it is the ordinary condition of the entire universe. When you look up at the night sky, you are not seeing the stars as they are. You are seeing the light they sent out years ago, centuries ago, in some cases longer than our whole species has existed. Some of those stars are already gone, burned out, and we simply have not received the news yet. The sky is a record of the past arriving on a delay. Every point of light up there is a letter from something that may no longer be. Cassini's death only made that truth small enough to feel. For 83 minutes, a spacecraft was already gone while we still believed it was alive, because the light carrying the news had not finished its journey. That is not an error in the universe. That is the universe. We are always, all of us, looking at a past we cannot reach, loving things across distances so vast that the present is something we will only ever learn about later. And what became of Cassini itself? This is what I find quietly beautiful. It did not crash into the ground and lie there as wreckage. It burned. It came apart in the upper atmosphere and scattered into the gas, its atoms mixing into the clouds of the planet it had circled for 13 years. Cassini is part of Saturn now. The metal that crossed more than 2 billion miles to get there is woven into the gold of the cloud bands, drifting in the winds it spent so long photographing from above. The explorer became part of the thing it explored. After 20 years away, in the only way left to it, it finally arrived. And out at the edge of that same system, the small white moon goes on exactly as it did before we ever came. Enceladus does not know what was sacrificed for it. It cannot. It simply continues, the way it has for untold millions of years. Deep under the ice, the buried sea presses against warm rock in the dark. The heat keeps rising. The fissures keep breathing. And from those 4 cracks at the South Pole, the fountains still climb. Silver columns of crystal lifting into a black sky and falling back as the softest snow that falls anywhere, with no spacecraft left to fly through them and no one there to watch. That was the whole point. We did not protect Enceladus so that we could keep studying it. We protected it by leaving it alone. The most precious thing Cassini ever found, it shielded by removing itself from the picture entirely, by making certain that the next time we come, the ocean will be exactly as untouched as the day we discovered it. We will go back someday. There are already dreams of returning, of a craft that could fly through the plume again, or one day drill down into the sea itself and finally ask whether anything is living there. The question is not closed. It is only waiting, kept clean, for a generation patient enough to answer it properly. Until then, the secret stays where it is, sealed under the ice, safe in the dark, held by a moon that orbits a planet that now carries, somewhere in its golden weather, the scattered atoms of the machine that found it and chose to let it be. Somewhere out there, right now, the fountains are still rising. No one is watching them. They do not need to be watched. The sea breathes. The snow falls. The great gold planet turns, slow and patient, the way it has turned for billions of years and will turn for billions more. And down in the dark water, under all that ice, the secret keeps. Quiet, untouched. waiting for us to be worthy of the answer.